Thank you very much for the chance to be here and tell you a bit about ExoMars. So, the title of the talk was supposed to be the exploration of Mars, but what I will really focus on is a search for life on Mars. So, we will discuss a few missions, but only in as much as they have served to move forward specific key topics related to the search for a possible, perhaps, past early life on Mars. And in order to address that, we'll have to touch on many subjects, dealing with physics, chemistry, and other things, and a bit also with what people think may have been the origin of life on Earth. So, let's start by having a look at the two planets. There's a number of things that are similar, like for example the inclination of a rotational axis, but Mars is smaller, and the one thing that sets it aside from Earth is the atmospheric composition, which is what we would associate with a pretty dead planet. A lot of CO2. And if we look at other aspects of Mars relative to Earth, we see, for example, that it doesn't have a magnetosphere, although we know it did have a magnetic field in the past. It doesn't have plate tectonics, at least at present it doesn't, and probably never did in the same way as Earth does today, so a multi-plate system, which on Earth is extremely important for recycling many of the contents of the atmosphere. We also benefit from the effects of a large moon, which stabilizes the oscillations of our rotational axis, and Mars doesn't have that, and at cycles of between 50,000 and 100,000 year periods, it experiences very wild oscillations of the rotational axis. And finally on Earth we have abundant liquid water available on the surface, which you know is a very important ingredient for life as we know it. One of the interesting findings of Mars Global Surveyor during its aerobraking campaign was that there was a remnant magnetic field signature preserved on the Martian crust. And it is preserved, as you see, mainly on the southern hemisphere, which is the older hemisphere of Mars. So these contains most of the Noachian terrains, is the part of Mars that stands basically 5,000 meters above the northern plains. And you can see here how the polarity of the magnetic field has been recorded on the crust material. Interestingly enough, this points to a pretty strong magnetic field that Mars had in the past. Now, if we look at what we have learned over the last 30 years by looking in our own little corner of our space garden, we have found a variety, a large diversity of worlds. And when it comes to life, it's interesting to ponder whether life is something probable or something very, very exceptional. And then when people talk about life and habitable worlds, we have to make a distinction about habitable by what. In the case of most of this talk, we're going to talk about microorganisms. Then habitable when. This is very important because planets evolve. They are not the same now as they were 4 billion years ago, and also our star evolves. And this has a large effect on the conditions on the surface of particular terrestrial planets. And finally, habitable where and when. We will see that conditions for the origin of life are very different from conditions for the colonization of a certain part of a planet, or conditions for survivability of something that may form spores, for example. So, habitable, finally, does not mean inhabited. We may have water, that doesn't mean that we're going to have life there. And So we are at a time, I would say the last 10 years, when a lot of the paradigms that we thought we felt comfortably about are being re-examined when it comes to trying to understand what may be the ingredients and the conditions necessary for life. So, how do people approach the origin of life? So basically there's two ways of doing it. One is backwards, and we start, for example, with biology or microbiology. We can also use chemistry and genomics. And the other way is to start forward, starting from, for example, the formation of the planets, physics, and somehow in the middle of all this falls geology, which is where the two things meet and where the conditions need to be present for things to happen. So we'll go a bit into some of these things. I'll just go very quickly about the early terrestrial planet evolution. It was, as we saw, a sort of a pretty dynamic environment where material was reigning in the forming planets. And the part that I pick up from the last two talks is I pick up where this, let's say, magma ocean enveloping the terrestrial planets starts to cool down, where material comes from the bottom up, and as it sees lower temperatures and pressures starts to degas, and these bubbles come up and form the primordial atmospheres, which, if you had been there, it wouldn't have been looked very nice. It would have looked maybe something like this. But the important thing is that the infant planets outgassed very large atmospheric envelopes. We're talking about several hundred bars of gas. And most probably these atmospheres were supercritical, like the atmosphere of Venus today. You know, above the critical point, gases don't know whether to be a gas or a liquid. They would like to be a gas, but the pressure is so hard or so high that it pushes the molecules into behaving more like a liquid. But the interesting thing is that as the atmospheres cool, eventually they go through a phase transition. When you go below the critical point of water, that water cannot stay in the atmosphere anymore. And basically you have a massive deluge. When you cross a critical point, the water that's up there rains down. And that's most likely how, in a very short time, the first oceans were formed. And these, we're talking about global oceans. There were still no emerged lands raining on the surface of the planet. And but this was still like a pressure cooker. The pressure was still probably above 100 bars, mostly CO2 now, nitrogen and a bit of steam, of course. And so you had this atmosphere, you had this global ocean that would start to cool down. And when things went below 80 degrees temperature, interesting for the ocean, interesting chemistry can start to happen. For example, 80 degrees is more or less the temperature below which ribose, which is a pretty important molecule for us, is stable. So basically we're talking about a phase when there was a lot of water, then the first continental masses started to appear, and this is summarized more or less in this graph, which from the formation of the solar system, basically here you have Earth, here you have Mars. You see here depicted graphically the story I just told you. Here you see the oldest preserved traces of life we have on Earth in the geological record. They're about 3.5 billion years in age. You see here more or less the age of the late heavy bombardment. You see the global ocean, the subaerial environment starting to appear. You see the ages here for Mars and for Earth. Very important though is the hydrothermal environment. These are planets that are still cooling down. There's a lot of heat coming from the interior, a lot of volcanism, hydrothermal activity, very powerfully acting under these infant oceans. In the case of the Earth, it's part of the process that recycled most of the CO2 into the crust to form carbonates. We don't know exactly what happened on Mars. Interestingly enough, on Venus, it is very possible that there might have been an early ocean as well. You have to consider that the luminosity of the sun was about 70% of what it is today 4 billion years ago, and that conditions changed the further away you were from the sun. For example, in the case of Earth, if we hadn't gotten some extra help, for example, from relatively higher amounts of CO2 and methane, the Earth would have turned into an ice sphere, an ice ball, because it was just too far away for what the luminosity was at the time. Even more so for Mars. Venus, the conditions would have been such that if you apply the black body equation, the temperature of the ocean would have been around 50 degrees or so. Now, on Mars things took a wrong turn more or less around here. We don't know exactly what happened, but we know that the magnetic field more or less turned off, and the planet very quickly turned dry, and basically conditions on the surface became what they are today rather quickly. So Mars quickly lost most of its atmosphere and became a frigid desert. But this period here is very interesting. There is a window of opportunity for life to have appeared on Mars roughly starting 4.4, 4.3 billion years ago. We don't know if it happened or not, but this is more or less the time when life appeared on our planet as well. So, now, what is the recipe for life? Now, a lot of people think that if you add organics to water, you get your chicken soup, but this is wrong. Just by adding organics into diluted medium, you don't create life. We will see now that you need very, very specific conditions. It's very complicated. Okay, so the next step is to look at what some of the definitions that have been proposed for what life is. And one I find very elegant is this one: a self-sustaining chemical system capable of Darwinian evolution. Now, can I design a space mission capable to check that there is Darwinian evolution on a self-sustaining chemical system? No way. So this is not a very useful information for us. The next thing is, there are some people who are actually trying to make life artificially in the laboratory. And these are the interesting people. Why? Because they do their alchemy, and at a certain point they have to be able to decide, is this alive or not? So they have a set of criteria, so to say, for deciding whether something is alive or not. And so we will look at that. So, the first thing is that it is not that clear to say that something is dead and then it is alive. Most probably, you become alive gradually by acquiring a set of functions. So, what is it that we need? We need a network of mutually supporting chemical interactions, and we will see what that means. That includes the following functions. So we will go backwards. We will look at the functions, and then we will understand whether this is fulfilled or not. First of all, a program. The program by which we are able to make the next generation. So we need a self-replicating information polymer. In our case, it's DNA and RNA that does its job. And these have to have a chemical catalysis function. which they do in our case. So we use monomers, and to make these monomers we need precursors, and these precursors we need to take from the environment. We'll see how this happens later. Second function, metabolism. Metabolism means I have to have a way to cycle between two energy states, one energy rich and one energy poor. For example, in a case of chemotrophic organisms, this is done by munching different valence states of elements. Here I mention iron. And you produce an electron which you then pass on to whoever needs to use it. Just for reference, you need about 100,000 electrons a second for a cell to work. Now, we need precursors as well, and these we need to get from the environment. Third function, containment. We need a membrane. This membrane also needs to produce a chemical catalysis function. In our case, this is lipids, phospholipids, which also need to be built from precursors that come from the environment. So, let us look at our minimal life system now. It has all these functions, and somehow they have to be synthesized from outside our life system. So, what do we need for this to happen? The environment has to have certain properties. We need the ability to complexate chemical substances. We need a proton gradient. And we need a flow, like in a gas chromatograph column. So, in the case of complexation, we need to, let's see, what did I write there? Combine, fixate, and enrich. We need something that is initially, at least, external to the microorganism that allows this to happen. In the case of a proton gradient, typically this is done by a difference in pH between the inside and the outside. And in the case of flow, you need a mobile phase, like I say, like in a gas chromatograph. And the environment has to be such that it is protected. It is particularly protected against the UV. It has a mild temperature. Because this is an experiment and you don't know where it's going to work and where it's not, you need to have this repeated in many places to have the chance that at least somewhere it's going to work. So, our system needs the following conditions to have existed for at least 1 million years somewhere on the surface of our planet for this to happen, for this machine to come about. So the conditions, we'll go through them one by one. The environment has to be UV protected, which is not a given for the infant planets. Second, we need a mild temperature. Third, we need slow solvent flow. We need complexation from a chemistry point of view to be possible. We need the environment to be ubiquitous and stable. We need organic precursors. And we need a proton gradient. Now, somebody pointed to me that if you get that machine that I mentioned about, and you can verify that you have that, then you have what the definition with the picture of Darwin said you needed. But I'm not going to focus on that, on how it came about. We don't know how life started on Earth, and my guess is that we will never find out. Maybe we'll get some clues on Mars, because Mars has much older geological material than our planet does. But what I want to focus on here is on the environment, on where life may have appeared. So, let's look first at organics delivered to an early ocean. Which conditions are satisfied? UV protected? Not if you are on the surface. Mild temperature? Probably. Slow solvent flow? Who knows? Complexation possible? Definitely not. At least not if you are in the bulk of the water. Ubiquitous and stable? Unlikely. It depends on where you are. Organic precursors, yes. The proton gradient, no. So just delivering organics to an ocean will not do the trick. Next one, the beach. The beach is very interesting because actually by having waves go on the beach and then come down, you actually run your mobile phase through a solid phase. So you actually have the possibility of enriching. So UV protected? No. Mild temperature? Possibly. Slow solvent flow? Yes. Complexation possible? Maybe in the grains. Ubiquitous and stable? No. Particularly if you think that when the moon was closer to Earth 4 billion years ago, the tides were much, much higher than what they are today. Instead of tens of meters, you have many tens of meters of tides. So the flow of the water on the beaches was wild. And the proton gradient, not necessarily on the beach. Let's keep on going. Subaerial hydrothermal systems on the first emerged land masses. The bad one here, but we're getting better, but the bad one here is a UV protected. If there was no oxygen on the primordial atmosphere, not much to speak of, there was no ozone, and so everything that the sun was putting out at the time in terms of UV was getting to the surface. So it's true that if you were in the shadow you were protected, but all in all there were not many emerged land masses, and the ones that were actually bathed in high doses of UV light. And finally, let's get to the good one. This ticks all the marks. Low temperature subaqueous hydrothermal systems, what we call today white smokers. Here you have it all. You have serpentinization processes giving rise to relatively complex organic molecules. You have these porous chimneys where the nutrient rich fluids are able to go through these very, very tiny capillaries and interact with minerals. So if you like, your food is flowing through, all you have to do is stretch your arm and grab it. So many of the conditions are present here, and the environment could have looked like something like this. This is from a recent paper by Francis Westall. And basically you have, of course there was delivery of organics. There is a lot of material coming from the volcanic activity falling in this ocean. You have your proton gradient, you have the alkaline stuff. The ocean was most likely acidic. Temperatures were mild. So this could have been an interesting environment. The reason why I talk about this is because if we're going to design a search for life mission, it's very important to figure out where you're going to look. So you have a number of options when you try to design a search for life mission. The first one is, do you go to a place where life could have developed? This means, can I land on top of a place where there was a submarine hydrothermal system where fluids were coming out at low temperatures? The bad news there is that hydrothermal systems are typically geographically very confined. They're only tens of meters across. If you have a ridge under the ocean, that's very high temperature. The low temperature hydrothermal systems usually are a few tens of meters to the left and to the right of the ridge. But they're not that easy to spot if you have piled, a couple of kilometers of material after they were formed and then eroded that. So the signatures for these on Mars, for example, are very tenuous. On Europa and any of the moons that may have a subsurface ocean where these may be going on now, maybe you have an easier job of finding them if you can get through the 20 kilometers of ice to go down into the ocean. The next thing you can do is say, well, I'm going to search in a place where life could have colonized and where life could have flourished. I don't know, a lake or a long-term I don't know, system of channels, or an ocean, if you can, a dried ocean, if you can find it. You don't know if there was ever life there, but if life appeared and somehow could have found a way there, maybe the traces could be found. And the last one, which is the one I like the least, is to search in a place where life could have collected. Now, geologists love this. They talk about their catchment basins. They love their catchment basins. But here we're talking about detrital stuff. You're talking about stuff that may have appeared somewhere else, and then the water brought it there, but you don't know how it came about, how the minerals were deposited. So this is, to me, is the poor man's option. And maybe that's all you can do, fine. But these two are much more attractive, because they give you the chance to try to find the microorganisms in the environment where they lived. Okay. So, what are the options? First of all, habitable zones. It is not sufficient to say that if liquid water was stable, we had life. We need much more for life to emerge. Second, the solar system is not typical. I took a whole bunch of slides to show you how the solar system is not your average run-of-the-mill planetary system, and how, to some extent, we should consider ourselves lucky to have all the water we have in the terrestrial planets. Now, life on Earth has colonized basically every single environment that it could reach. But that doesn't mean that it could have emerged in many of these extreme environments. And in the outer moons, it seems that these submarine hydrothermal systems may be quite typical. So let's see what we can do with all this stuff. First of all, there's another important point that I want to make here. We look at Mars because we think that many of the processes that were important for the origin of life on Earth may have been active also on Mars very early in its history. It is a hypothesis, of course we need to check it. The second thing is that because Mars didn't have plate tectonics, we can find places where we can land on Mars that are 4.1 billion years in age, where the rocks that were deposited 4.1 billion years ago are still there in a pretty good state of conservation, at least from a geological point of view. This is something that we can only dream of on Earth. On Earth it's extremely difficult to find rocks that are older than 3.5, 3.6 billion years in age that haven't been heated up beyond 400 degrees. So Mars is a place where we may even be able to learn something about our own planet. Mars may have been like this in the very beginning, and they may have been like this. So, we talked about habitability, which is the ensemble of conditions that make a place favorable, for example, for the appearance of life or for life to flourish. But we also need to talk about preservation, because the stuff we want to look at needs to have made this 4 billion year trip in a good state, otherwise we won't be able to understand what it is we're looking at. So we'll spend some time discussing that. Another thing I want to mention is that if you can design a mission to look for past life, which means the degraded products of something that may have lived 4 billion years ago, that was buried, entombed, that underwent diagenesis, So all the processes that happen since deposition until we find the place. If you can put together a mission that can do this, then it's very easy to do that, to detect present life. Because in this case, all you have to do is look for the Lego bricks of living cells. And these are much easier to detect and understand than these ones. And finally, as if the problem were not complicated enough, you have the delivered organics of meteoritic origin. We have about 300 tons of carbon that rain on, organic carbon that rains on the terrestrial planets every year, and this has nothing to do with life. These are cosmic organics. So, let's look a bit about missions that have tried to search for life. The first one is the Cadillac of the skies, the Viking missions of 1976, which on today's euros would have been something like 10 billion euros. These were amazing missions, and you have to think that when they put these things together in the late 1960s, there were no computers, there were no integrated circuits. They did everything with discrete components. The most complicated thing they had were transistors. And yet they had robotic arms, gas chromatograph, mass spectrometers, the works. These missions were really, really ambitious, and they taught us loads about Mars. So, for example, we found out that there was a lot of water on the surface of Mars. We found out that there was a lot of buried ice under Mars. Here you see a crater on the moon, and here you see a rampant crater with these lobates. Lobate deposits that point to ice being present in the subsurface at the moment of impact. We got the first images of the surface. They even went and looked for life, and they did this in a very clever way. Unfortunately, since I didn't have time, I stripped out the slides of how the metabolic experiments worked, but basically what they did was they had 3 instruments looking for the metabolic response of living microorganisms. At the time, scientists were thought that it would be very probable that Mars would harbor living microorganisms at the surface. So they designed these 3 instruments to look for respiratory and metabolic responses from the microorganisms. And they were very smart. They also had parallel experiments where they heat sterilized the samples to 600 degrees, and in that case they would get no response. And the answers were pretty puzzling, because a couple of instruments gave results that would have indicated the presence of life. The decider was that the gas chromatograph mass spectrometer, which ironically was not a life-seeking instrument, failed to detect the presence of any organic molecules. We see that this is not true. But this put a hiatus in Mars exploration for almost 15 years, because Mars all of a sudden lost most of its allure as a target. The next big contribution came from our little European Mars Express. For a long time, people knew that on Earth, most of the organic fraction is associated with the tiny particles. And they thought, well, if we have all these materials that reacted with water, particularly if we had pyroclastic deposits, mafics, ultramafics, there should be clay somewhere. And why is it that none of the missions until then have detected clays? And then since 2005, I'm going the wrong way, the Omega instrument on Mars Express has detected many instances of clays. And then when MRO joined a few years later with higher resolution, they confirmed the clays, and they also saw that the clays occurred only in the most ancient terrains, pointing again to the fact that ancient Mars was wet. The next important result for the search for life came from Phoenix in 2008. Phoenix landed in the subpolar regions of Mars, and for the very first time ever had a wet chemistry experiment. So they put a bit of Martian dirt in solution and looked for cations and anions, and much to everybody's surprise, they found the presence of perchlorate. Perchlorate is a pretty exotic salt, and for example, we use it as oxidizer in rocket fuel, ammonium perchlorate. The trick here is it's stable, it doesn't do anything, it's pretty inert until you heat it up. When you go above a couple hundred degrees, these oxygens dissociate and they become very powerful oxidation vectors, and basically they combust or oxidize what it is you're trying to look at. And then the same thing was seen on Curiosity, and then people started to scratch their heads and remembered that on Viking in 1976 they had detected chloromethane and dichloromethane, which at the time they thought they were residues from the cleaning agent. But today what we know is that Mars is chock full of perchlorates, and when you heat up your samples, when you try to detect the organics, you activate them, and then they react with the organics and give you chlorinated species. So, with this, we move into ExoMars. This is everything that we had to use, or we could use, in order to prepare the mission. How am I doing with time?
Still have half an hour.
Okay. So, ExoMars is a joint venture between the Russian Federal Space Agency Roscosmos and ESA, with some very important contributions from NASA. And it has two missions. I will not talk a lot about ExoMars 2016. It is basically a big nose in the sky. It is, its main goal is to search for trace gases. So these are gases that exist in minute quantities, typically below 1%. And one of the main targets of interest is methane. We also had a capsule which, as you know, crashed on the last 45 seconds prior to landing. And if any of you is interested in knowing why, I can tell you later. So that didn't work. But the orbiter is doing great. We went through 1 year of aerobraking, and we came out of aerobraking in April of this year. And then one of the largest dust storms ever to hit, well, the largest at least in the last 15 years, arrived. And so for the last couple of months, we haven't been able to take very many great pictures. We think we will start lifting up around October. But all the instruments are working well, and we are in the scientific orbit. So we will start coming up with results very, very soon. The first ones concerning methane will be in the EPSC in September this year. So the interest in methane comes from Earth, because on Earth, most of the methane on our planet, roughly 75 to 80%, is a result of life. Of course, it's not the only way to produce methane. You can also do it through geological processes, and most interesting among these is a family of processes between mild to hot water with some ultramafic minerals that is commonly known as serpentinization, which produces hydrogen, which then can react via other reactions, like Fischer-Tropsch reactions, to produce methane and other organic gases. I won't talk a lot about that. I'll just tell you that the instruments we have is we have two clusters of infrared and UV spectrometers, a high-resolution stereo camera, and a neutron detector for determining or mapping the presence of subsurface ice below the surface. We get 10,000 times better sensitivity than previous missions by working in what is called sun occultation mode. You basically use the sun as a very bright infrared light bulb. So the signal to noise ratio is astronomical when you look in this configuration. So we can do parts per trillion in terms of sensitivity. Of course, when we look at the surface, where you're looking at reflected infrared light, then the signal to noise ratio is pretty bad, and then our sensitivity reduces to 10 parts per billion or so. On the top you see what was here expanded, the sensitivity of Mars Express when it did its methane detection, and this is what we can do with NOMAD, our instrument, one of the two instruments, an ACS and TGO. And here you see the families of gases that we can look at. These have to do with atmospheric composition. This has to do with water escape and history, although MAVEN can do this much better. This has to do with organics and methane and its other products, and this with volcanic activity. And we can also do ozone. And just some pretty pictures. It's always nice to show a bit of hardware. And I'd rather move on to the next mission, which is the one I've been working on for the last 15 to 20 years. So this has two science elements. There's a whole bunch of instruments on the lander that I will show in the next slide. And then the rover has for objective to search for traces of past life on Mars, and we will see how this is done. Just so I can be sure to talk about this, because this is the only slide on the surface platform. There's 11 Russian instruments and 2 European instruments devoted to geophysics and the environment. And then instead the rover, you will see that the front is dominated by a drill, and we will see now why this is so very important. In the back you see the so this is maybe bothering. In the back you see the ground penetrating radar antennas. This little window is where a small hand comes out to collect the sample that the rover picks up from below the surface. Now we'll move up to the mast. That's where the cameras are and an infrared spectrometer. Here you see the antennas, the navigation cameras. I'll now show you a bit of what's inside. You see the drill needs to assemble a number of shafts to reach its full depth. The front is dominated by the analytical laboratory drawer, which has to be ultra clean because that's where the organics detection is performed. In the back you see the service module. This is the battery pack, the 2 radioactive heating units, 2 transmitters, inertial measurement units. These are the instruments. Here's that little hand I was discussing. There's a rock crusher. We will discuss all of this stuff in a second. So this is just to show you that this is not just only models, it actually exists. That's here you see the analytical laboratory integrated, that's a service module. This is the structural and thermal model that is finishing its tests now in Toulouse. Now the interesting thing, now we'll go through the instruments. You have to remember that the mission has to go from panoramic scale, so 100 meters to tens of meters, all the way to molecular scale. Because the mission is not about physics, is not about geology, it's about organic chemistry. And we will see why this is the most important set of biosignatures we can go for. So, all the measurements have been conceived as nested measurements in scale. So you go from large to small, but each measurement is embedded in the previous one. So we start with the cameras. The cameras, we have a stereo pair that see like a 50 millimeter objective on your camera, and then in the center there is one single high resolution camera that is like a 300 millimeter objective. And this allows us to obtain images with this field of view and embedded in them the ones with higher magnification. And co-registered with a high-resolution camera, there is an infrared spectrometer, because on Mars everything is orange-brown, and so this gives us an idea of the bulk mineralogy of the targets. You can imagine that if we need to decide whether we go to A, to B, or to C in terms of targets, it takes us many days. So it's interesting to gather information of the environment around the rover and then be able to say something about faraway samples or targets before we commit to go there. On the way, it is very important that we map what happens in the subsurface. You will see that the drill is capable of obtaining samples down to 2 meters in depth, but it takes us 5 days to drill 2 meters. And just for indication, the deepest that any of the NASA missions has gone so far is 5 centimeters. These 2 meters, as we will see, is a big deal. And we also have a ground, besides the ground penetrating radar, which gives us the vertical stratigraphy with a resolution of 2 centimeters, we have a neutron detector that tells us what is the degree of humidity. This is very important when we crash the samples. We want to have an idea of how much water they contain. When we get close to a target, one of the major classes of biosignatures is structural biosignatures. We cannot see individual microorganisms, particularly if they are simple chemotrophic. They typically have a size less than 10 microns per individual microorganisms, but we could see colonies. And we could see, for example, on Earth you have some biosedimentary edifices like stromatolites, for example, or some of the polymer mats that you see on beaches. Those, if they were preserved in the geological record, we could try to investigate with a close-up imager. The close-up imager is very interesting because it can look in a whole bunch of directions, and it focuses between 10 centimeters and infinity, so depending on how far away you are from what you're looking at, you can get resolutions in the order of, we can go down to 8 microns per pixel on the sample after we have collected it, but typically at about a meter distance we are still in the order of 80 microns per pixel. Now, the drill, very important, is like a mini oil platform. We have to assemble 4 shafts in order to go all the way down to 2 meters. It has an infrared spectrometer integrated in the drill tip that looks through a sapphire window on the side and gives us the mineralogy as we go down. This is very, very important. Mars has many bad things, but one of the good things it has is that it's very, very cold. And we will see that this is very important for the preservation of some of the more labile components. You see the drill here. This is the sample when it comes up. We can look at it with a high resolution camera and also with a close-up imager. Let's look at what happens in the analytical laboratory. We get a sample. It's typically 1 inch by 1 centimeter in diameter, and it gets crushed. The first thing we do is we deliver it to an instrument called micromega, and what this does is it looks at the sample, which is now crushed mineral grains, and instead of taking a picture that is RGB, red, green, and blue, it's a picture that is red, green, and blue plus 350 more or less spectral steps in the infrared. And so we have a computer inside the rover that looks at this and analyzes automatically the mineralogy of the various grains. And this information then we use to move the sample tray under the point and shoot instruments. In that way we're able to obtain infrared, Raman, and organic measurements exactly on the same mineral grains, which is very important. And besides this way of desorbing organics with UV laser, we also have 32 ovens, as Viking did and Curiosity did, that are able to perform interesting chemistry. So if you look at cosmic organics, you more or less see a continuous distribution with many of the little molecules and relatively fewer of the larger molecules. Instead, life doesn't work like that at all. Life specializes. It builds what it needs. So one of the interesting things that we can look at with MoMA, which is a wide or a range detection instrument is we can look for islands, or what we call clusters of organic molecules. We can also look at the relative spacing of these peaks, because this is a very important signature of enzymatic activity. Typically, for example, when you build fatty acids, the enzyme replicates always using the same template. So if you see certain separation between the peaks in a chromatogram, for example, this is very important. We can also look at chirality, which is another interesting property of organic molecules. We know we have left-handed amino acids and right-handed sugars. So if we see it has to be a large enantiomeric excess, because you also have some enantiomeric excess in meteorites, and this has nothing to do with life. But if you have a very marked enantiomeric excess, that's also a very important biosignature. So this instrument is the heart of the mission. It has a larger mass than all the other instruments put together, and a nice price tag of more than 100 million euros. It's the most expensive instrument we have ever worked on. But on universities, about the size of this desk, and on ExoMars is about this big. Okay, 15 minutes? 10 minutes? Okay. Let's look at what MoMA can do. This is organics detection instruments relative to other instruments. The first thing I told you is that for the first time we will use UV laser to extract or to desorb organics. No other mission has done this, and this is super important because this is the one technique that doesn't suffer from the presence of perchlorates. The deposition of energy is so fast that the perchlorates don't have time to liberate the oxygen. So we are able to extract the organics and analyze them without exciting the perchlorates. Now, we also have the more classical way of doing things, which is to use gas chromatography. We have 4 columns, one capable of chiral analysis and 3 other ones. And typically what you do is you use the ovens, you heat them up, and you extract by thermal volatilization. But here we have the problem of the perchlorate. So what we're doing is we are using a whole bunch. We can do pyrolysis, which is just heat, but we also have these derivatization agents. These are, when you have a little molecule that doesn't want to become gaseous, what you do is you associate a very large buffalo of a molecule to it that you know very, very well, which becomes gaseous very easily, and then you're able to render volatile the pair, and then you analyze the combination of the 2 molecules. That's what you do with this wet chemistry with derivatization agents. And just to give you an idea, this shows you where the O gets released from the perchlorates at what temperature. And so, for example, this one for chiral amino acids, we can use it at low temperatures, so we're able to extract the amino acids without getting them destroyed by the perchlorates. So, we have a little system to try to convince ourselves or not that we have found life. And so we have a scoring system, and we have provided scores for different types of biosignatures. You could use this for any mission, to go to Europa, for example. Now, if you could detect all of these, you would get 200 points. We are telling you that if you can score 100 points, you have proven that you have found life. And we have tried this on 4 samples, 2 Martian and 2 terrestrial. And on one of the terrestrials, we barely get to the limit. It's very, very difficult even to get the 100 points. Now, the things that have a gray background, we cannot address on the mission. So we don't do isotope analysis on ExoMars, and we cannot image individual microfossils. This is something that you could do on Earth if you were able to bring the samples back. And one other thing that is very, very important, the first thing you have to do when you land on Mars is you have to run a blank check through your organics instrument to be able to prove that you haven't brought any organics with you from Earth. Only after you have proven that you are squeaky clean, you can start your chemistry mission. But what you can see from here is that most of the score is on the chemicals. The chemical biosignature is extremely important. Okay, very quickly. Why do we care about the subsurface? This is the breakdown of organic molecule composition on a cell. Let's say Escherichia coli, which is a pretty typical one. We all have it. And what you find is that most of the organics are in the form of amino acids. Of course, you have all these proteins everywhere, and they inhabit the bulk of the cytoplasm. So they are in the volume. These, however, are very liable. They're very easy to destroy. In fact, after, the same goes for the nucleobases that are part of RNA and DNA. After a microorganism dies and all the organic components are released into the ground, these guys disappear relatively quickly. The ones that are the hardiest are the lipids, which is what membranes are made of. But look how many, 0.7%. Now, these guys, they tend to hang around for billions of years under the right conditions, but there's not that very many. So what can we do to see if we can also target these guys? So let's look in the subsurface. Why? Because it's cold. It's like a freezer. The temperature during the day is 0 degrees, the temperature at night is minus 120 degrees, and the temperature, if you go 50 centimeters below, is the average between the two, minus 60 degrees. It's better than a freezer, it's great. So your organic molecules, provided they're not destroyed by ionizing radiation, will sit there waiting for you for a gazillion years. So, but radiolysis destruction is really a problem. It follows a very simple law, where this is the molecule abundance after radiation, the molecule abundance prior to radiation. That's a radiolysis constant, which is different for every molecule, and you have to calculate it if you want to find out what it is. And that's the cumulative radiation dose, which is over the entire lifetime of the molecule after it was deposited. So what can we do with this? We want to calculate that. We need to estimate these two. The important one is, how do we find out what is the dose? Now, we were lost until 2014 when Curiosity, which has a radiation detector, actually measured these. Before then, it was just models. And we started to work on ExoMars way before that, so I will show you how things changed. This is the work that got it all started. What you see here is a mixture of peptides, a mixture of amino acids being exposed dry in a glass vial to gamma radiation as a means to simulate being in the Martian subsurface for 500 million, 1 billion, 2 billion, 3 billion, and 4 billion years. And this is a surviving fraction. So that's 1. If you get no exposure, that's 1,000 times fewer molecules. He gets really dismal very quickly. And this is the burial depth. So, when we started, we said, what is... I mentioned already that we want to be able to look at amino acids because they are 63% of the dry mass of organic components in cells, because they are the only ones that preserve biochirality, and because they can survive for billions of years if they are protected from radiation. So, when we started, we thought we could sustain a degradation of 10 to the minus 3 relative to the original presence of organic molecules on the rocks and still be able to detect. So we said, we need to drill. If we want to detect something that was alive 4 billion years ago, we need to drill at least to a depth such that we can detect this. So we said between 1.5 and 2 meters. Then, when Curiosity landed, things were not so bad. The curves moved there. So it looked like now we could get by with less than 1.5 meters. But work on Earth also progressed. So analysis from some of the oldest rocks on Earth showed that the organic composition is in the order of 10 to the minus 4. If we assume that all of those are amino acids, which is not true because most of this is polycyclic aromatic hydrocarbons and gunk, but let's assume for the sake of argument that these 10 to the minus 4 are amino acids. If I have a parts per billion detection instrument, to be sure that I detected organics, I need to detect at parts per million. And this means that I need to detect there. And that means, again, that my depth is closer to 2 meters. Now, the interesting thing about organic molecules is that the larger the organic molecule, the faster it degrades. Why? Because it's just a bigger target. This ionizing radiation is like bullets being fired, and it just cuts your functional groups of your molecules. So if the molecule you're interested in detecting is large, you see that the curve moves to the right. So basically these 2 meters, between 1.5 and 2 meters, has stood the test of time. Okay, this is just to summarize again, this is how the sample is obtained. It's a little sample, it's collected up, is delivered there, is analyzed. The lifetime of the mission nominal is 7 months. During that time we expect to analyze in the order of 20 samples. We expect to look at 6 places, a few hundred meters apart. This is not a mission like Curiosity where we expect to travel long distances. We want to land on the science. And we want to spend roughly 1/3 of the time moving and 2/3 of the time analyzing samples. And this is the reason why we go to 2 meters. We want to go below the oxidants and the ionizing radiation degradation horizon. If you are interested in knowing more about this, there's a special issue of Astrobiology describing all of the instruments and the mission. It came out in July, August last year, or June, July last year. This is a summary of the instruments and the main countries behind them. And I want to finish by spending 2 minutes on the landing site, because the quality of the landing site is paramount to what we're going to find on this mission. So I mentioned that we're going to analyze 6 places, and on 2 of those places, if we find something interesting, we want to do what is called vertical surveys, which is on one place we collect samples at 0, 50 centimeters, 1 meter, 1.5 meters and 2 meters to see how things change with depth. But this is an operation that takes us in the order of a month and a half. So we want to be sure we do it somewhere where it is important. So let's look at what we need in order to achieve the science. We need a place that is old. How old? Well, we say at least 4 billion years. We want to go somewhere also where we can land with the parachutes, so it has to be relatively low. These are the latitudes we can target, and this is the only place on Mars that gives us ancient terrains that are Noachian at the right altitude. So we are concentrating on that part, and these are very large fields of clays, and we have selected 2 sites, which are Marth Valleys and Oxyaplanum. They both contain large terraces with a couple hundred meters of stacks of layered clays. You can think of these clays as sort of the rings on a tree. Every one of those layers records an instance of deposition and wetting. And interesting is that in Oxyaplanum you have access to only the base part of the stack, and in Marth Valleys you have access to everything but the lowest part of the stack. We think there's a good chance that this could have been the bottom of a very large sea or lake on Mars, for a number of reasons that I will not discuss today. And what I want to do here is place this in perspective with the other graph I showed you before. All the missions that have landed on Mars until now, including Curiosity, have landed here or younger. So we are the first ones, and I think Mars 2020 will do it as well, to try to target this very early part of the Martian history. There are some nice things that the rover has also from the point of view of technique. I just want to show you one movie, which is that the rover can wheel walk. Means that we can use the wheels as wheels, but if we get to very sandy terrain, very loose, so we need to climb very steep slopes, we can also use the wheels as feet. This is lower, but allows us to negotiate very steep inclines. So for example, this came about after a Spirit got trapped and couldn't get out. If we were in such a situation, we would engage this mode and we would be able to get out. So lessons learned from our NASA colleagues. This is actually a Russian invention, by the way. So 25th of July, I'm sure they will press the button if everything is okay. The landing is on the 19th of March 2021. So we go with a cruise stage with a very large capsule, and we land on legs because that's the way the Russians do it. And we have 2 ramps, so we can go out in either of 2 directions. So this is to show you another bit of hardware. This is the heat shield. That's the structural and thermal model of the lander. You see the engines here, the radar altimeter. This comes from Schiaparelli, one of the things that worked okay. We have a very complex set of parachutes. We have the largest parachute that will ever go to Mars. This is true to scale. That's the Statue of Liberty, including pedestal. That's the ExoMars subsonic parachute. We tested this at the beginning of this year, and we're going to launch it again in August from a high balloon. And just to finish, we are pretty excited about this mission. We are very, very interested both about what the surface platform will be able to do in terms of understanding the present environment of Mars, but particularly about being able to travel back in time 4 billion years and explore what we hope will be, or will turn out to be, the bottom of a large sea or body of water on Mars, and search for the first time for organic molecules in a place where we trust they will be well protected. I have a good shot at trying to find out if there is a chance that there may have been life on Mars. I give us 50-50 in terms of being able to say anything conclusive. I am convinced we're going to find organic molecules because Curiosity has found them already, but I think that the easy pickings close to the surface are meteoritic. To be able to have a shot at biogenic organics, we'll have to look in the right mineral matrix. And here we know we have large stacks of clays, but what I'm really, really interested in is in hydrothermal veins. Because on Earth you have much larger biomasses there because simply there's more nutrients, and they could have been also an interesting place for the origin of life. And finally, a very important point, you know that Mars 2020 is going to cache samples, but it's going to cache samples from the surface. If we find that the juicy stuff lies in the subsurface, This may give us pause and may cause us to consider sending another mission to cache also subsurface samples to bring back to Earth, because on Earth we can do much better than we can do on Mars with robotic means. Thank you.